For the second circuit, it's the RLC circuit, the low pass filter. The input is connected to a resistor and in series with an inductor and a capacitor. We'll be using the same inductor and capacitor values we used in the first problem. So I used a 2.7 millihenry and the 10 nanofarad for the resistor. So the critical resistor, or the resistor that gives a critically damped response, is 2 times square root of L divided by C. And I got 1 kilo ohm. And to get the underdamped and the overdamped response, I chose the 330 ohms for the underdamped and 3.3 kilo ohms for the overdamped. So here's the circuit. Here's the input from the function generator, and it's connected to R in series with 2.7 millihenry in series with the capacitor, and then to the ground. The output is across the capacitor. This is broken. Here's the output. And again, since we use the same L and C values, so we have the same resonant frequency value, which is 30.6, and to set up the function generator, it's F naught divided by 12, which is 2.55 kilohertz. So here's the output, and this is the 330 ohm, which will give the underdamped response. For the RLC circuit, here's the transient response you got. So the yellow represents the underdamped, and it matches what we got on the oscilloscope. Now, to check on the frequency response of this circuit, in PSpice you have the AC sweep, and it gives you the behavior of the circuit along the range of frequencies. So here it's from 100 hertz to more than 1 megahertz, but here in the lab we can only measure it around one frequency. So to measure the frequency response of this circuit, I'll start at this point at the 100 hertz, and we'll notice the peak to peak to the output voltage. What happens to the output voltage? Let's go faster. So the output voltage seems to increase. This is the max, which is around 30.6, and then after that it decreases again to 0. This explains what you got in the pre-lab. So the yellow waveform here represents the AC sweep for the underdamped. The green here, the green waveform, is the input voltage. And we can say that the input voltage here is 2 peak to peak. So the output voltage, be peak to peak 2, below the resonant frequency, is exactly the same or around the input voltage. And once you increase the frequency, the peak to peak 2 starts to increase, and it reaches the maximum around the resonant frequency. And we notice that peak to peak 2 reaches its maximum around 30.6, which is the resonant frequency of this circuit. And then above the resonant frequency, peak to peak 2 starts to decay to 0. This is for the first circuit, which is the underdamped circuit. Now let's check the critically damped. So for the critically damped, we need to use the 1K. Here's the 1K. Let's go back to the 2.2 kilohertz. And here's the output for the critically damped, and it matches the purple waveform here, like what you got in the pre-lab. And then to check the frequency response of this circuit, I'll go back to the 100 Hertz for the purple waveform here. For the frequency response, I'll go to the 100 Hertz, and we can see that peak to peak 2 equals peak to peak 1 at 100 Hertz. While I am increasing the frequency, peak to peak 2 is decreasing. Decreasing to 0. This explains the purple waveform here. So when we started, at the 100 Hertz, peak to peak 2 was equals to peak to peak 1, which is the purple, and the peak to peak 1 is the input voltage, which is the green one. And as we increase the frequency, peak to peak 2 drops to 0. The same is going to happen with the overdamped. So let's try the third circuit. For the overdamped, we have the 3.3 kilo ohms. Let's go back to 2.2 kilohertz. Auto scale. So here's the output, and this output matches the red waveform here. Now to check the frequency response of this circuit, we'll start with the 100 Hertz and the function generator. And we can notice that peak to peak 2 equals peak to peak 1. And then as we increase the frequency, peak to peak 2 starts to decay to 0. This explains the red waveform here. This is for the RLC circuit, the low pass filter.